We are given this quadratic function, f of x equals x squared plus 2, and we are asked to find the inverse. As you know, this is a right side up facing parabola that's been shifted vertically up 2. So when we do that, we perform the algebra. The first thing we do is we replace f of x with y. We switch the x and y, and we solve for x. And when we get to this point down here, and we take the square root of both sides, we have to remember to take the plus and the minus version. Now here's the problem. When we go to graph the inverse function, we see that it fails the vertical line test. So here we have our original function, y equals x squared plus 2. And when we go to graph the plus minus square root of x minus 2, we see that this is not a function because it fails the vertical line test. And that's because the original function is not one-to-one. The original function, shown in red, while it passes the vertical line test and therefore is a function, it fails the horizontal line test, which means it's not one-to-one, which means when you take the inverse graph will not be a function. So because of this, what mathematicians have done is they've restricted the domain of the quadratic function first, and then you find the inverse, so that the inverse itself will indeed be a function. So let's see what that looks like. Let's graph the original function, x squared plus 2, but limit the domain to where x is greater than or equal to 0. And when we do that, we get this function here. You could see the x is limited to where it is greater than or equal to 0. Now, if we were to take the inverse of that, we would get one of these two limbs only, and the resulting inverse graph would indeed be a function. But here's the question. When you graph the inverse of the original function with the restricted domain, which of these ends up being the inverse function? Is it the plus version or the minus version? And that's what this video is about. And the short answer is as follows. If you are limiting the domain to where x is greater than or equal to 0, you're going to use the positive version of the inverse. So here we go. I have selected only the positive version of the square root of x minus 2, and you could see these inverses match. I forgot to graph the line y equals x. Let's go ahead and do that now. As we know, inverses will be reflected over this very famous line, y equals x. And you could see that when we restrict the domain of the original function to x is greater than or equal to 0, it's the positive version of the square root function that is indeed going to be the inverse. Now, with respect to the short answer of what happens when you restrict the domain x being less than 0, it turns out we're going to use the negative version. So let's do that. Let's graph the original function where the domain is limited to where x is negative. It turns out that we're going to pick the negative version of the inverse, negative version of the square root as its inverse. So in summary, if the x is limited to being positive, you're going to choose the positive square root version. If the x is limited on the original function to where x is negative, you're going to pick the negative version of the square root. And as we'll find out, folks, this same dynamic holds true even when there's a negative in front of the original function. In other words, the fact if you put a negative in front of that original function, it does not change things. If you take this a value being negative and you say you want to limit the domain to where x is greater than or equal to 0, you're still going to use the positive version of the inverse function. If you limit that domain to where x is less than or equal to 0, where x is negative, then you're going to use the negative version of the inverse function despite the fact that there's a negative in front. And for the remainder of the video, I'm going to show you the intuition as to why this holds true. To discuss the intuition as to why, when the initial domain is restricted to x is less than or equal to 0, we're going to choose the negative version of the square root. And when the domain is restricted on the original function to where x is greater than or equal to 0, we're going to choose the positive version of the inverse function. Let's first discuss the end behavior of square root functions as controlled by the signage. So here on the upper left, we have a plus outside the radical and a plus inside. That means the end behavior of this graph is going to head towards where x is positive and where y is positive. And that is none other than the first quadrant. So this plus sign means the first move is up from the vertex, and it's going to continue to where the y value is positive. Okay, here, when the combination has a plus outside and a minus inside, the graph's end behavior is going to head towards where the x value is negative and the y value is positive. That's going to be the second quadrant. So again, because of that plus sign, the first move is going to be up, and then it's going to continue to head where the y values are positive. Coming down here, this graph is going to head, end behavior is going to be towards where x is positive and the y value is negative. That's going to be down here in the fourth quadrant. So we're going to get to the vertex. Because of that minus sign outside of the radical, the first move is down, and it's going to continue where the y values are negative. Over here in the lower right, we have both negatives. That means this graph is going to head towards where the x values are negative and the y values are negative. That's going to be in the third quadrant. So again, we're going to start at the vertex here. Because of that minus sign that's outside the radical, our first move is down, and then we're going to continue to where the y values are negative down here in the third quadrant. And as we'll see, this graph analysis of the radical functions is the key to analyzing why this is true. And specifically, we're going to focus on the sign that's outside of the graph, because this is the signage. That's the sign that's going to control the end behavior with respect to the y value. So here, look, outside of the radical, we have a positive sign. The end behavior is a positive y value. This is heading towards positive infinity. Here, on this side, that sign is positive. Again, the y value is heading towards positive infinity. Down below, negative outside. This graph, the y value's heading towards negative infinity. Over here, again, outside negative, the y value's heading towards negative infinity. It doesn't matter what's on the inside. What I'm focusing now is the y value. That sign outside the radical determines whether the y value of this graph is going to head towards positive infinity when it's positive out front, or negative infinity when there's a negative out front. Next, let's talk about the intuition as to why this is true. And what I mean by this is true is the following: that if we restrict the domain of the original quadratic function where x is greater than or equal to 0, where x is positive, where x is heading towards positive infinity, that means when we have to make the choice between the positive or negative version of the square root, we're going to choose the positive version. And here's why. Recall, when you have a function and you take its inverse, the domain and the range switch. So on our original function, we restricted our domain to x is greater than or equal to 0. So x is between 0 and positive infinity. You see it here. X is between 0 and positive infinity. The range is going to be y greater than or equal to 2, or the y value goes from 2 towards positive infinity. Now when we switch, we're going to take the range y is greater than or equal to 2 and make that the domain x is greater than or equal to 2. We're going to take the original domain x greater than or equal to 0. We're going to make that the range of the inverse function where y is greater than or equal to 0. So folks, which one of these graphs match? None other than the yellow graph. You could see the range of the yellow graph goes from 0 towards positive infinity. The same thing that the domain of the original function went to. So therefore, we're confident that we could erase this function and focus only on the positive value. Now, let's see what happens. Let's see if this holds true if we put a negative in front of that x squared term. If we have an a value that is negative. Where here, we've placed a negative in front, and then we went ahead and took the inverse, as we always do. We swapped the x and the y. We eliminated the negative from the y squared before we took the square root, and we're left with y equals plus or minus 2 minus x. The question is, which version are we going to take, the plus or the minus? Folks, again, if that original function, if the domain is restricted to where x is positive, where x is greater than or equal to 0, where x is heading towards positive infinity. Look, here's the domain. X is greater than or equal to 0. X is heading towards positive infinity. That means the range of this function, of the inverse function, has to be where y is headed towards positive infinity, where y is greater than or equal to 0. And recall from our discussion previously, that is determined by the sign on the outside of the radical. So again, we're going to choose the positive version of the inverse, even though there's a negative out front. Why? Because the original domain was restricted to where x is positive. If the original domain is x is positive, then the final range has to be where y is positive. That mandates a positive on the outside of the radical. Let's now review this on Desmos. This is our original function, x squared plus 2. No restrictions. We know that if we took the inverse of this, we would get a parabola on its side that is not a function. So as a result, we proceeded to restrict the domain. So let's first look at where we restricted the domain, where x is positive. Now, when we take the inverse of that function, we're going to get a choice between the negative version and the positive version, because the original constraint, the original domain is restricted to where x is positive. We're going to choose the positive version, and we're going to graph y equals x to show that was the correct decision. Okay, let's start from scratch again, and now let's restrict our original function to where x is negative. Here we go. X is less than or equal to negative. X is negative. Now, because x is negative, we're going to choose the negative version of the inverse. And here we see the negative version of the inverse. And again, with y equals x, we could see that they clearly are inverse functions. Okay, folks, now let's switch to where we put a negative in front of the x squared term. Our a value is negative. Let's see if that changes anything. Okay, that's our original graph with the restriction of x greater than equal to 0, x positive. Here are the two versions of the inverse function. We predict that because the original constraint is limited to where x is positive, we're going to take the positive version of the inverse. And there we go, it matches. Okay? In summary, that negative does not change the rule. If the original x is constrained as positive, meaning greater than or equal to 0, then the inverse that we're going to choose is the positive version. Folks, here's the reason why choosing an a value in front of the x squared term of being negative does not change the choice of the inverse function. Here we have x squared plus 2 where x is restricted to where x is positive only. The domain of this red function is from x equals 0 to x equals positive infinity. Now, when we put a negative sign in front of the quadratic term, the domain doesn't change. This domain in blue, where there's a value that's negative, is still x equals 0 heading towards positive infinity. Therefore, when we go to choose the inverse functions of both of these, here when our a value is positive, we choose the positive version of the square root, because while the domain of the original function, x was heading towards positive infinity, we now want to choose an inverse function where the y values change, trending towards positive infinity. And then when we use the negative version, when we put an a value that's negative, again, the domain is the same as when a is positive. X is heading towards positive infinity, therefore we're going to choose an inverse function where the y value is heading towards positive infinity. Don't let this fool you. The fact that the inverse graph shown in red is heading this way doesn't change what the y values are doing. The y values are still heading from 0 to positive infinity. Just like the domain of the original function, x is heading from 0 to positive infinity.